Hello student, welcome all of you on our YouTube channel, Department of Mathematics, Sanjeevanee Mahavidyalaya, Chapoli. Student, this is a lecture for BSc first year student, semester first, and our paper is Differential Calculus. This is our 8th lecture. In previous lecture, 7th lecture, we have discussed about the relation between continuity and differentiability. In previous lecture, we have discussed if the function is derivable, then it must be continuous. And for their correspondence, we have taken one theorem. We discussed it in detail. Now today, here we are going to discuss about its converse. There is no doubt, if the function is differentiable, then it is continuous. But what will be happen if the function is continuous, but we can't say about their differentiability, whether it is differentiable or not. So in general, if the function is continuous, then it may or may not be differentiable. Need not be necessary that if a function is continuous, then it will be differentiable or it must be differentiable. We discuss one example. Suppose we discuss one example. Y is equal to mod x. This is our function f of x. So y is equal to mod x with the function and which is continuous to every point on its domain if the domain is a real number or any domain. We get y is equal to mod x is a continuous function. If you draw the graph of this function, that means when your x is equal to 1, then y is equal to 1, like that. When your x is equal to 2, y is equal to 2, like that. And for the x is equal to 0, we get y is equal to 0. If we take minus 1, we get the 1 again because it is the absolute value function. And like this, we get the V-shaped graph. And we observe that here everywhere on its domain. What is domain? Domain is a set of real number R. So on its domain, the function y is equal to mod x is continuous everywhere. So it is clear that this function is continuous. Now we are going to discuss about its differentiability. Let this our function f of x is equal to mod x can be redefined as mod x. So value of this function is minus x when the x is less than 0, 0 when x is equal to 0, and x when the x is greater than 0. That means for the x is greater than 0, this function is positive, and for the x is less than 0, our values are minus x, and when x is equal to 0, we get 0. This is the mod function or absolute value function. We check left hand and right hand limit at x is equal to 0. So here left hand derivative and right hand derivative I am going to check. Left hand derivative. So left hand derivative at x tends to 0 is f of x plus h minus f of x divided by h. So this is equal to limit h tends to 0 minus. So for the x is less than 0, for x is less than 0, value is minus x. So that is minus of x plus h minus x divided by h. And computing this left hand derivative, so limit h tends to 0, we get here minus x minus h and minus plus x divided by h. So after computing this, we get limit h tends to 0 minus and minus h divided by h is equal to minus 1. So here left hand derivative of the function is minus 1 at x is equal to 0. That means x tends to 0 or h tends to 0, no problem. Next, we discuss about the right hand derivative. And for the right hand derivative, limit h tends to 0 plus f of x plus h minus f of x divided by h. And limit h tends to 0 plus, what is the f of x plus h? So for the 0 plus, that means x tends to x greater than 0, and for the x greater than 0, our function is x. For the x greater than 0, our function is x. So here we take x plus h minus x divided by h, plus x minus x get cancelled. And here limit h tends to 0 plus, we get h upon h, and h upon h is 1. H upon h is 1. So here right hand derivative. So right hand derivative is 1. We observe here that right hand derivative 1 and left hand derivative is minus 1. So if right hand derivative is not equal to left hand derivative, then the derivative of that function does not exist at that point. And therefore the function f of x, that is our y, is equal to mod x is not differentiable. So from this we conclude that if the function f, our conclusion is that if function f is continuous, then f need not differentiable. So this is very important concept in the calculus. Students, you can check for the more examples, but this is very famous example and therefore I discuss it. So in previous lecture we have discussed one theorem, and that was if the function is differentiable, it must be continuous, but it's vice versa not true. That is, if a function f is continuous, then f need not be differentiable. So try to understand it. In next lecture, we will discuss about the geometrical meaning of differentiability. So thank you very much.